here. Today and tomorrow, we'll talk about the law of sines, and maybe at the end of the period tomorrow, introduce the law of cosines, and then talk about law of cosines for Wednesday, bulk of Wednesday and Thursday, and then we'll have a Chapter 8 test on Friday. Okay. I was hesitant to even give a chapter test over this stuff, but because we're close to the end of the 9 weeks, okay, I want to give you an opportunity to get another large grade and do well on it. But I didn't want to give a take-home that could potentially inflate that grade too much. Okay, so I want your grades to, or they should reflect our knowledge, and sometimes those take-home tests maybe don't do that. So that's the plan. This stuff is not entirely difficult. There are some aspects of it that are hard, but I'm going to try to my best kind of get you through those. One aspect of law of sines, which is very, I think, confusing, is actually more of an ACT type question, which obviously that is one of my goals, is for you guys to perform well on the ACT. We'll introduce that tomorrow. I don't know how many examples, because they take about, to get through one in class, takes about 25, 30 minutes to do one. So we might kind of just introduce that, not necessarily do a lot of examples with that. But the end of course exam will not ask you about that situation, or at least in the last 5 years they have not, and I will not ask that situation on test on Thursday. Okay, but I do want to introduce it to you so you can see what's happening. But this stuff is, so we know right now, if I gave you a right triangle and I asked you to find distances and angle measurements, you can do that using SOHCAHTOA, right? And the only reason we can do that is because of essentially the right triangle properties. Okay, we talked earlier in the chapter about how sine, cosine, and tangent, those relationships exist because we have similar triangles with right triangles. Okay, so any right triangle has a 30-degree angle. I know the sine of that 30-degree angle is always going to give me an opposite side divided by a hypotenuse in a 1-to-2 relationship. That's always going to be true. So that's why sine, cosine, tangent work in right triangles. But what happens when we get to, because right triangles are only a very small portion of the number of triangles that we work with, right? What if I'm working with like a non-right triangle, like this one up here? Then how do I find missing side lengths? And what I want to do here is walk you through the demonstration that generates our formula that allows us to find distances in non-right triangles, okay, and angle measurements as well. So this is a non-right triangle. We can mess around with this thing, move it. At least I thought I could. Maybe I can't. So it looks like I made this several years ago. But this represents an infinite number of triangles. Any triangle that you want to make that is non-right, okay, so none of these are right angles. Maybe convince you of that. So obviously that's not a right angle, right? Maybe the only one that people would think could potentially be a right angle is this one up here. And that's 291. That would have to be 270 degrees for that to be 90 degrees. Does that kind of make sense? So that's not a right angle either. So it's a non-right triangle. What we're going to do is play off of our knowledge about altitudes. How many altitudes does every triangle have? Well, let's remind ourselves what an altitude is. Anybody remember what an altitude is? Yes. Okay. Good. So I'm going to start at B, and I'm going to go perpendicular to the opposite side. That's an altitude. Okay. Starting at a vertex and then perpendicular to the line containing the opposite side was the definition that we used in Chapter 4. Now, that altitude then would be, get in here, there we go, that one. Okay. So I'm going to look at that altitude. Okay. We know that exists. That is a segment that is 100% there inside this non-right triangle. Okay. That generates this red triangle. Okay. If I want to look at that red triangle, my question to you is, can you, if you focus on this angle right here, okay, what would you call H? What side would that be? Opposite. And what would you call C? The hypotenuse. Okay? So can I write a relationship that says sine of capital A is equal to H over C. Does that make sense? Is that fair to say? Okay. So that is from what we know about right triangle trigonometry. I want to do the same thing then, but instead of looking at angle A, let's look at angle C over here. Okay. What side would H be for angle C? It'd be opposite again. And now what would A be? It would be the hypotenuse in this orange-colored triangle, right? Okay. Now B is that distance right there, right? So B is not part of that orange triangle. Okay. So I'm not looking at that distance. But can I say now that maybe sine of C, sine of capital C, is equal to H over A? Does that make sense? So that's just looking at some relationships that we know should exist inside those two red triangles. Now here's something that I want to think about. And when we did this a little bit, we talked about this Thursday, I believe. Remember that question I gave you about like Mars, the crater on Mars or whatever? And we essentially broke it down into two right triangles. And we found that distance. And we found that distance and we added those together, right? Okay. What we just did here is ultimately part of that question, what we did in that question. Okay. So the law of sines, what I'm trying to get at there is the law of sines would have been a nice tool to have for that problem because it would have saved it would probably cut our work down probably in half, if not more. Okay. But now what I want to do right here, if we look at those two triangles, would you guys agree that H is part of both of those triangles? Okay. So whatever H is in this formula here, it's the same as what H was in that formula, right? Let's take one of these, and it doesn't matter which one we do this with. Let's take one of these equations and solve for H. Okay, so let's just take this first one. If I were to solve for H, what do I need to multiply both sides by? Multiply by C. So I need to always multiply by LCD, right? Least common denominator. So multiply by C, that's going to cancel. Come over here, I get C. So it's going to be C times sine of capital A is equal to H, right? Now remember, the H, right here, that H, is the same as the H over here, right? Can I replace that right there with that H, or in the spot of that H? Does that make sense to everyone? Just using substitution here. So I'm going to have sine of C is equal to, now this H is going to become that thing. So C times sine of A divided by A. Okay? And that's nice, and then that is actually a relationship that is true, and that is the law of sines, but we can make it a little bit better. Okay? Notice over here that this portion here is capital A and lowercase a, right? So it's this angle paired up with the side that's opposite it, correct? Okay. Let's see if we can make this so that's the only thing that's left on that side. So what can I multiply this side by so that this C here disappears or cancels out? It's going to have to be a fraction. Or what could I divide this side by so the C goes away? Divide by C, right? So I'm going to multiply. So dividing by C is the same thing as multiplying by the reciprocal of C, right? If I did that, so if I just do this, if I had like 2x over 3, and I wanted to cancel that 2, what do I multiply by 1/2 so that they cancel like that? Does that make sense to everybody? So same idea. Now that 2 is just a C instead. So multiply by 1 over c, so they cancel there. Come over here and multiply by 1 over c. So I get 1 times sine of c, which would be that. C times 1, which would be that. And then what I'm left with on the right-hand side is just what's in yellow. So sine of capital A over lowercase a. And the nice thing about that structure is, again, going back to looking at C, and it's paired in a fraction with the side that is opposite it. Does that make sense? Okay. So at capital A, the sine of capital A divided by the side that's opposite, the sine of capital C divided by the side that is opposite. There's one more thing that we're going to get here. What do you think we should end up doing eventually with capital B? I want to have a third. It's really big. I'm going to have a third ratio here. It's going to be sine of something over something. What do you think should go in that parenthesis right there? Capital B, and what should go down here? Lowercase b. So that and that were opposite, right? And the reason for that, I'm not going to get into how we generate this third one too much. But the reason for it is we could have actually looked at that altitude instead. Does that make sense? That altitude would, going through the same algebra that we did here, that altitude would eventually get me that the sine of B over B is equal to the sine of C over C. And we use then the transitive property. If we look at those two things, and I guess these two black ones we had, do they both have sine of C in them over C? So then I can do the transitive property of sine of B equals sine of C over C, sine of B over B equals sine of C over C, and sine of C over C equals sine of A over A. Then all of these things are true. Okay? But what I want to get at with you right now, what I want you to get out of this, if I close this out real quick, is the law of sine is the sine of an angle divided by the opposite side equal to the sine of a second angle divided by its opposite side. That's all we need. We only need two of these ratios to create an equation that's going to allow us to solve for whatever our variable is. Okay? So a lot of times, even though they write sine of C over C, you can put that in there, but it doesn't matter. Okay? All we need is two angles and two sides, and they have to be opposite one another. Okay? And that will set that ratio. Now, because of what we know about working with proportions, you know, we can change those two. We can flip flop those two if we wanted to, and still get true proportions. We can take reciprocal. Usually, the rule that you see a lot of times, other than this one, is like A over sine of A equals B over sine of B, and that's just taking the reciprocal of both sides, right? So you can do that. All of our proportion properties are still in play here. Okay, but when we're in class, I'm going to predominantly use this one. I think Math Excel will use that one the most, and of course Exam uses this version, and that should always be true. The only triangles that this works in are triangles that follow, I think I had it here, these three orientations of parts. Okay? So if they give me, I'll just give you an example of what angle side looks like. They're going to give you, let's say this angle here. I'm just going to put marks on these angles. I'll just kind of highlight them this way. So I'll give you that angle, and then that side. And you can use angle, side, and the law of sines will allow you then to find missing distances and missing angles. In this situation, if they give me this, if they give me these two angles, I automatically know that angle because of the triangle angle sum theorem, right? Okay. Basically, what this one's going to allow you to do initially, you know, these two things you know. Those are going to have numerical values with them. This one here, you're going to know. Well, if I'm thinking about the law of sines, then this purple angle at top, will have to pair in its ratio with that red angle, or red segment. Does that make sense? So this would be maybe where my variable is, and I'll solve for x. Okay. Angle side angle is going to look like this. In regards to the parts that they give you, they'll give you that angle, they'll give you that angle, they'll give you this side that is in between them. You know, these angles, I'm drawing them with congruency symbols that are different, but they could be the same angle. Okay, that could happen. Same measurement, they could be congruent. In this case, okay, you don't know the side opposite this angle, and you don't know the side opposite the top angle. But if they give you these two angles, do you automatically know that one? So now the sides that you would have, you'd have this side opposite of that angle, so that would be one ratio. And then this would be like x, and you could say the sine of this angle that you know, opposite that variable. Okay. When you have, so this is angle side angle. When you have these situations, guys, if I were to give you these purple angle measurements and that purple distance, and I gave everybody the same length of segment and the same measurement of angles on their table, gave you maybe like a yardstick for the segments and maybe cardboard cutouts for the angles, and I said, make a triangle out of this information. Every one of you, because of what we talked about in chapter 4, every one of you is going to get the exact same triangle. Does that make sense? Because angle, side congruency guarantees that. Okay? If I were to give you this purple angle, that purple angle, and a yardstick for that segment right there. Okay, so the purple angle is again made out of cardboard. Everybody gets the same two. Everybody gets the same distance. Everybody gets the same yardstick. And I ask everybody to make a triangle out of that information. Every one of you is going to make the same exact triangle, right? Nobody's going to have a different one. Okay? If I were to give you this relationship, side-side angle, okay, I give you, so let's kind of draw that real quick. So they're going to give you that side, and an angle that is not in between them. If I gave you all two distances, everybody has the exact same two distances. Everybody has one angle, and I tell you, you've got to set them up that order. There will be varying triangles, okay? They will not all be the same. Does that make sense? Okay? And that's because the side-side angle doesn't guarantee congruency, okay? But we can still use the law of sines with it. It's just a case that we're going to spend a little bit of time on tomorrow, okay? I remember this, so, and just trying to draw your attention to this so we remember, this, if we reverse the letters right there, okay, ASS, right, okay, that's a orientation of parts that is difficult to work with. It's a pain in the butt. Does that make sense? Okay, so ASS equals butt, right? Okay, so that's how I'm going to have you guys remember that when we get to a picture or a structure of parts that are angle side, that's a pain in the butt because it almost doubles, if not triples, the amount of work that we have to do for it. Okay, it kind of stinks. Okay, that's why it's a pain in the butt. So all the other ones, pretty straightforward. Those are going to be pretty straightforward to work with. This one, we've got to do some thoughtful process with. And tomorrow, I want to try and show you kind of the physics of the two different triangles that could show up, and then why we have to go through a certain process to see if we have multiple triangles. Okay, so angle side produces multiple triangles, a potential for multiple triangles or multiple answers, and that's not something people enjoy. Okay, but that's more of a, like I said, that's more of an ACT level type question. Okay, this is a majority of the problems that we're going to see are going to be of this format, but I'm going to just draw that picture right now, draw that triangle, and I'm going to remove some stuff to clean it up a little bit. So the sentence at the top just gives me a setup of that triangle with the information that's in it. So you don't need to write that down. Just like I said, just draw the picture. And we're going to then ask to find the length of BC. The length of BC. One thing I want to make sure we understand is that obviously this is not a right triangle, right? 93 degrees, that's an obtuse angle, so I cannot have a right angle in there with an obtuse angle, okay? So I know angle C is not 90 degrees. So when it's a non-right triangle, I'm going to try to set up the law of sines. So law of sines says the sine of an angle divided by the side opposite is equal to the sine of another angle divided by the side opposite, okay? Just for us in this case, it's just nice that A, B, and C are letters being used, but they don't have to be A, B, and C, okay? That's why I like to say an angle, the sine of an angle, and then the side opposite, okay? So I'm going to say sine of 48. You agree that would be an angle, right? The side opposite that is X is what we're looking for, correct? Okay. I know when we started this, I didn't even think that this was angle, side, and I'm going to try to convince you of this process. I always, no matter what, if I know it's a non-right triangle, I'm going to try to see if the law of sines works. I'm going to try to see if I can set up a proportion where I only have one variable in that proportion. Okay? If I have two variables in that proportion, it tells me law of sines does not work, and then it tells me then law of cosines will work, and that's what I would turn to, and we'll talk about that later this week. So I'm just trying to create a proportion with one variable. Do I have a variable so far in my proportion? So the next ratio has to have numerical values in both spots. Okay? So I'm going to put sine here, but what's in the parentheses has to be a number. What is the number that I get to use? 93. Okay? And then what will be the side that is opposite 93? 15. Okay? And the argument here is we should know that what is that angle right there? What's 93 plus 48? That 141? Okay, so this angle here should be 39 degrees, correct? If I put sine of 39 here, would I know what value to put underneath it? Do I know the opposite of 39? So that would be two variables. Does that make sense? So that's maybe a way of knowing that I don't use the 39, I use the 93. Okay? I like to, and you're going to see me do this when we do examples, I like to kind of like circle those two things and then link them. And I know those go together in one ratio. And then I'll circle or highlight or whatever these two, and they will go together in one ratio. Okay? And I see that kind of that cross created through highlighting like that, and that reminds me law of sines works. Okay? How do I solve a proportion? What's the first step? Okay, so I'm going to multiply these two, right? I'm going to cross multiply. So we get 15 sine of 48. And then we're going to cross multiply these two, right? So we get x sine of 93. Is that okay with everybody? Okay. Now just remember, and this is where I get a lot of people get confused, but if you just sit and think real quick, what does this mean? That is a symbol for another number, right? So all I've got over here on the left-hand side is two numbers being multiplied together. I've got a product. If sine of 48 is a symbol for a number, then that must be a symbol for a number, right? Sine of 93 is probably like 0.9 something, okay? Well, let's actually see if I can get Desmos to give me sine of 93. Sine of 93, 0.998, right? So when I say x times sine of 93, I'm really saying 0.9986 times x. Does that make sense? So this here is my coefficient, but it's rounded. This is my coefficient, unrounded, right? Okay. So how do I solve for this variable, x, if sine of 93 is my coefficient? Divide by sine of 93. Good. And we're going to get x equals, so it'll just be then 15 sine of 48 divided by sine of 93. And we're going to grab our calculator and input that. Make sure that you're using the right mode. So I know I'm in degrees right now. I think I changed it just a moment ago for us. So I am in degrees, so that is the appropriate answer. Now just think about it. I mean, I've told you this time several times. If we're in radians, you might be able to see an answer that's just like, well, that's blatantly obvious that that's wrong. Right? A lot of times, the way that you would see it is that it gives you back a negative number. Okay? If you're in radians, sometimes it'll give you back a negative number. But in this situation, with this particular problem, if I'm in radians, it gives me back 12. That's really not all that crazy compared to the 11.16, right? So I might be doing things, and that's 15 was this distance, 12 is reasonable to that 15. Maybe I think that's my answer. Always, 100% of the time, every time you hit the sine, the cosine, or the tangent buttons on your calculator, glance at what the mode is. Get in the habit of doing that. Because you could do, like I said, you could do everything 100% accurately, but be in the wrong mode, and then your calculator gives you the wrong answer, and the state says you're a terrible math student because you hit the wrong button on your calculator. Does that make sense? Okay? So make sure we're paying attention to the mode. Is that something we can do? Okay, last class, I know we've been talking about mode for a while here. Last class asked, what is a radian? So I think it may be appropriate to kind of show you guys what a radian is as well. And of course, exam, and we'll spend a little bit of time on it beyond today, but they have in the past asked about radians, so we will discuss this a little bit more. But this is what a radian is. So I'm going to take this distance here. Okay, that is the only distance that is required to make a circle. Okay, circles are one-dimensional shapes. Does that kind of make sense? Okay, in regards to the radius is the only thing that determines them. Create my circle. Okay, so that's my radius. Let's call it radius R, but it could be anything that we want it to be. It could be 2, it could be 5. When we get to trigonometry, we want it to be a 1 because it makes things really nice. Okay, but now I'm going to take that radius and I'm going to keep it the same length, but move it on the outside of my triangle or my circle. Okay, now I'm going to take that length and bend it along my circumference. Okay, so that distance right there, let's say that my radius was, let's say that was like 3 feet. Then when I walk from that point there to that point there along the circumference, it's still 3 feet. Does that make sense? It's just a bent distance. Is that right? You can walk a mile on a straight path or you can walk a mile on a circle, right? Okay. So that is my radius bent around my circumference. When I connect my vertex right here, or I guess the center of my circle, to these 2 points, you create an angle, right? Okay. Now, roughly, so the first quadrant is 90 degrees, correct? So this would be roughly about 60 degrees, and I believe it's about 57 point something degrees. That angle right there is what we consider to be 1 radian. Okay. Now, why do we have radians and we have degrees? And it's because of what's going to happen next. It's just it's a little bit easier to deal with radians than it is to deal with degrees. Because when I put in 3 radians, so I just cut and paste that angle 3 different times, there becomes this little sliver right here. That little pink sliver, okay, which would be another angle that we need to add to 3 to get this half of a circle, okay, this semicircle. When you guys think about circles, what's the number one number that you think about when you think about circles? Okay, what's the second? I heard it over here. 3.14. So 360 is a common answer. So maybe I phrased it incorrectly, but 3.14. and that is pi, right? So when we think about circles, we think 2 pi r, we think pi r squared, right? Okay. Pi is the number we get when we take the circumference and divide it by the diameter, right? Okay. Of any circle. Well, when I continue to mark this off, that angle right there, which is how many degrees? 180 degrees, right? Okay, that's half the circle, correct? So that angle will be 180 degrees, but it's pi radians. So 180 degrees is equivalent to pi radians. Okay? It's kind of like saying 1 inch equals 2.54 centimeters. You guys know that, right? Okay? That allows me to go from the U.S. customary system to the metric system, yes? This allows me to go from degrees to radians. Okay? It's a conversion factor. Now, what's convenient about this is, well, if I go all the way around 360 degrees, that gives me 2 pi radians. Does that make sense? Okay. What's the circumference formula for a circle? 2 pi times how many radius? 2 pi r, right? 2 pi times your radius. So in trig, we like to make our radius 1 so that this circumference here becomes just 2 pi. And we work with that circle a lot. Okay. But here's why things become a little bit more useful using that approach. We know that, let's say we're in degrees, we know sine of 30 is 1/2. So every triangle has a 30-degree angle and it has a 1:2 ratio of the opposite side divided by the hypotenuse, right? Okay, that's what that is saying. If I take 30 degrees and I change it to radians, so my conversion factor was pi radians equals 180 degrees. So to get into radians, I need to multiply by this. Because the 30 has degrees on it, 180 has degrees on it, pi has radians on it. Those are going to cancel, those degrees are going to cancel, and it's going to leave me with that. Does that make sense? Okay. But first, so let's just write it this way real quick. 30 pi over 180, is that the same thing as 3 pi over 18, which is the same thing as pi over 6. Does that kind of make sense, everybody? So 30 degrees is equivalent to pi over 6 radians. Okay? How can I prove that to you? Well, let's go type in sine of pi over 6. Okay? If 30 degrees was the same thing as pi over 6, then this number should be the same as that number, right? Does that make sense? But remember what our calculator is in. Our calculator is in degrees. So it's only working this one accurately. Right now it's saying I'm looking at 0.52 degrees here. Let's change this into radians. And you see this number go to 0.5, right? Okay. So pi over 6 radians and 30 degrees are equivalent. Okay. And that's something that right there is like the first week and a half of trig. That's what we do in that course. Okay. And then when we start asking, what is the sine of 120 with degrees, we see that it's 0.866, which is the square root of 3 divided by 2. Or in radians, we say it's 2 pi over 3. So let's change my calculator to radians, and we should see that same 0.866 number show up. Okay, so that's a little thing about radians. I don't think we know enough geometry yet to really get to that point, but we've been saying what radian, or talking about radians, make sure we're in the right mode. We want to make sure that everything we do right now is in degrees, okay? And the radian aspect of the calculator is using that pi over 6, 2 pi over 3, those types of things that are adjusting these numbers, okay? Let's draw this picture. Don't write any of this verbiage out. Just write the picture down, and we'll do another example. See the stock market today?
No, it didn't go down.
They had to pause it this morning. They just stopped it, canceled it, because canceled all trading because it had taken a 2,000 point dive. So they stopped it because the 1930s. They didn't stop it; it just kept going, right? So my brother told me not to look at my stocks. So I'm gonna look at my stocks right now, see how much money I've lost today. Oh, that's bad.
That's a lot of money in this stock.
Huh?
You put a lot of money in this stock?
Like I have a Roth IRA, and yearly you're only allowed to contribute $5,000 to it. So I have one. My wife has one. We put $10,000 in every year. But I lost $10,000 today. So.
Yeah.
But so I'm not gonna take that out for it's for my retirement. So I'm not gonna retire for another 30 years. So for me, it makes sense for me to actually go put more money in today, because now I can buy stocks at a smaller price, right? And then they'll recover. So these prices that they currently are at, they'll recover, and I will make money off that then. But it's kind of yeah. But I also think that the media is heavily Democratic, and I think part of it's the virus, but I think also part of it is the media perpetuating the virus. I don't think the virus is as bad as what the media is saying it is, but the media knows that the Democrats only have Joe Biden and Bernie Sanders to be president, and they were both crazy. Joe Biden can't tell his wife and his sister apart from one another. He endorsed Trump 3 days ago on purpose, or I guess on accident. Did you see that? Your dad actually posted it on Facebook. Yeah, I know. And then Bernie Sanders won't tell you how much things are going to cost. He's going to tax it. He's going to give you free education. But do you know what that means? Your education will be free, but what you work for is going to get taxed, and your money that you're going to take home isn't going to be there. They're going to take it. And then I'm going to pay for your education. Does that make sense? Or they're going to cancel my educational debt. But the way they cancel it is to raise your taxes. So you might have chosen not to go to school, and you don't have debt, but they raise your taxes so that you can pay my debt. Does that make sense? So that's what he wants to do. And he doesn't have any idea how much that's going to cost, because it's trillions of dollars. But the media knows that those two guys can't beat Trump. So let's perpetuate this coronavirus thing and shoot the stock market way down, and then Trump doesn't have a stock market to run off of. That's my opinion. I think that's what they're doing. And also, I think the coronavirus, they can't, if they have the coronavirus, they're scaring people into not going to his rallies. And if you can't have his rallies, you can't get his numbers up, that kind of stuff. But that's just my opinion. So I do think the coronavirus is real, but I don't think it's as bad as they think. But the market tanked today because Saudi Arabia started making more. Russia and Saudi Arabia are, I don't know, in a tussle with each other. So they shot up their oil production when it's not necessary, the demand for it is not needed. But so they ended up making more on purpose, and it dropped gas prices 30%. So if you go home tonight, gas is probably going to be $1.89. Okay, hasn't been that since I was in the third grade. So I mean that's good for us as drivers, but it killed the economy. It's killing Italy's economy. It's killing Greece's economy right now. Greece might even fall out of the EU because of Saudi Arabia just making more oil than what's needed for that. They're just putting more oil into the market than what is being demanded for. So prices went down. Markets flipped out. So there's a lot of things going on there. Today is actually a pretty historical day for the market. It's kind of Black Tuesday. This day kind of if they wouldn't have stopped it, maybe it could have been something like that. Okay, so sidetrack, sorry. When we set this one up, we're going to take sine of 120, because that's an angle I know, right? And what is the side opposite it? 18, correct? Now, if I'm going to be able to use the law of sines here, I've got two numbers you can use over here. I need a variable on this side, right? 11 is a known value. I'm going to use 11, and that's going to have to go on, because that's a segment distance, so it's got to go in the denominator. Would you guys agree that 11 is opposite that angle there? And I don't know that angle. So that is actually my variable in this situation. So what they're giving me here is angle side, and this is actually the pain in the butt situation, but it's only going to, we're only going to look at it through this perspective. So we're not going to do the second triangle that could exist here. But I'm going to have then the sign of that angle. And I'm going to make a dollar sign there for my S, because sometimes my S's look like 5s. So that's an S, okay? So now, if I want to solve this, I go through the exact same steps that I went through on the previous example. Hunter said we need to cross multiply in the previous example, right? Let's do the same thing. So I get 18 sine now of my angle S is equal to 11 times my sine of 120, correct? Okay. Now, remember, when we have an angle being what we're looking for, we're trying to solve for that S right there, okay? I need to isolate that. I need to get that by itself. So what is the number I should divide both sides by in order to get to that point? Okay, they're close. This whole thing right now is kind of my unknown. Okay, so I'm going to divide by 18. Those cancel out, leaves me sine of this angle now is equal to 11 sine of 120 over 18. Now do you remember how, when we were working with SOHCAHTOA, how we get that angle out? We have to use the sine inverse. So I'm going to say sine inverse of both sides. And on the left-hand side, it's going to leave me with just, so I go sine inverse here and sine inverse here. I'm going to get S. And then this side will be sine inverse of 11 sine of 120 divided by 18. These things can be kind of a pain in the butt to type in, and they're really ugly if you use your little red calculators or blue ones, or your TIA 3 or 4. My suggestion: get comfortable using Desmos. That's going to be what is going to be available to you if you don't bring your own calculator on an intercourse exam. And I think that's a benefit to you if they're letting you use this, because that's how I wrote it by hand, right? So if that's how I wrote it by hand, I know I typed it incorrectly. Now I need to change the mode to degrees. You guys get 31.95 as the degree of that angle. Does that make sense? So once I know that angle is 31.95, was the one angle was 120, so I've used that many degrees, right? 151.95. Can I subtract that from 180 to get the third angle? Does that make sense? Okay. So what they usually ask you to do is, once you start finding one segment length, one angle measurement, is in the keep rolling with that. Find the next angle measurement. Find the next segment length, and find all. What they'll say is solve the triangle, which means find all 6 parts of the triangle. Okay. All 3 angles and all 3 side lengths. But it's then, once we find one distance or one angle, you can usually use other properties like the triangle angle sum theorem or something like that to help you finish off the triangle. Tomorrow, we'll spend a little bit of time on maybe doing 1 or 2 of these generic, basic, cookie cutter problems, and then maybe some story problems.